So, have you ever stopped to wonder how we control some of the most powerful chemical reactions on Earth? I'm talking about things like launching rockets into space. It's not magic, not by a long shot. It's software. And today, we're going to pull back the curtain and see exactly how it works.
All right, first things first, let's frame the challenge here. This isn't your high school chemistry experiment. We are talking about calculations where the stakes are, well, astronomically high.
I mean, really think about it for a second. How do engineers know, for sure, what's going to happen when they ignite literally tons of rocket propellant? Getting it wrong? That's not an option. So, how do they nail it? Every single time.
While the answer isn't guesswork, and it's definitely not risky, expensive trial and error, it all comes down to incredibly sophisticated simulation. See, this is the key. This predictive software transforms what would be a high-risk physical experiment into a safe, efficient, and unbelievably precise digital design. Before even one drop of fuel is ever ignited, the entire reaction has already been mapped out, right there on a computer.
So what is this magic tool? What is this thing that professionals rely on for these absolutely critical simulations?
It's called CEA. That stands for Chemical Equilibrium with Applications. And to understand this powerhouse of a program, we're going to do something kind of cool. We're going to unpack the whole thing by focusing on just a single sentence from our source material.
And here it is. I know, it looks dense, it looks super technical, but trust me, this one sentence has everything we need to know. Our whole mission here is to break this down piece by piece so that by the end of all this, it'll make perfect sense. Okay, let's get into it. We're going to decode this by breaking down the key terms in that sentence, and that's going to show us how CEA actually works. First up, you see two big concepts in there: chemical equilibrium and combustion. Now, they sound related, and they are, but they describe very different things. Combustion, that's the action. It's the fiery, rapid process of burning. But equilibrium, that's the stable, balanced state the chemicals reach after all the fireworks are over.
So what exactly is chemical equilibrium? You know, the easiest way to think about it is like a tug of war, where neither side is winning. It's perfectly balanced. That's equilibrium. It's the stable point where the reaction has finally settled down. And CEA's whole job is to calculate exactly what that final balanced state is going to look like. But you know, to make that calculation, the software needs ingredients. It needs data. That's where thermochemical data comes into play. This is the raw information about every chemical involved, how much energy it's holding, how much energy it took to create it. You can think of it as the fundamental recipe book that fuels the entire simulation.
And if that thermochemical data is the input, the ingredients we put in, then combustion properties, well, that's the output. That's the final dish. These are the results we actually care about. How hot is it going to get? What will the pressure be? CEA takes all that raw data and predicts these absolutely critical outcomes.
Now, let's connect all these dots back to the real world, specifically with fuels and propellants. This is the so what moment. This is the reason this software is so unbelievably important. This right here, this is exactly what engineers are looking for. They're using CEA to predict the final temperature and the resulting pressure inside a rocket engine. They can figure out the potential thrust it's going to generate and even what the chemical makeup of the exhaust will be. These aren't just wild guesses. They are precise, calculated predictions. So how does an engineer actually use this thing? Well, it's a pretty logical process. First, they tell the software what they're mixing together. You know, the fuel and the oxidizer. Step 2, they set the starting conditions, like the initial pressure. Then they hit run, and CEA does all the heavy lifting, calculating that final equilibrium state. And finally, they get to analyze the results and see if the performance is going to meet their goals. So now that we get the what and the how, let's talk about the why. Why is this predictive power so transformative? Let's jump back to our original sentence for a second. Notice it doesn't say the software is sometimes used or occasionally used. It says it's widely used. That little phrase tells us everything. It tells us that CEA isn't some niche academic tool. It is an industry standard. It's fundamental to how this work gets done. So, here's the crucial point. When we look at this sentence again, it's not just a string of jargon anymore, is it? We can actually see the whole story now. A widely trusted tool uses fundamental energy data to predict the outcome of incredibly powerful reactions for critical applications like rocket propulsion. We've totally cracked the code. And that brings us to a final thought. We've just seen how simulation lets us master complex chemistry with just staggering accuracy. So it kind of leads to a bigger question, right? If we can do all this for chemical reactions, What other incredibly complex systems, I'm talking about climate patterns, biological processes, are next on the horizon for this level of predictive mastery? What do you think is the next frontier?